Okay, so right here is a little review of what we've talked about for sound waves. And I want to look at this image closely. So here's a source of sound. My favorite source of sound, of course, is a drum. And the waves move through the air to a person's ear, and then that activates a whole series of events that allow us to hear the sound, which is itself a very interesting study, although that's part of biology. So we're not going to go there about how it works from the ear into your brain. But let's look at these waves. Now, most of the time when I think of waves, I don't know about you, but I think about waves on a lake, right? Something like that. And this is actually very much like light waves, but it's not so much like sound waves. There are similarities though. What's happening is that some form of energy, often on a lake, it would be the wind, or it might be a boat that created these waves. At any rate, some form of energy is moving through the water, or whatever it might be. The air, space, whatever it might be. In this case, the energy is moving from left to right across the surface of the water. And as that energy is moving from left to right across the surface of the water, the energy is actually going in the opposite direction. It's a disturbance, and in this case, it is going up and then down. So waves on water have this disturbance that's causing them, and it's pushing the water up and down, but this disturbance is moving to the side across the surface of the water. And we're going to talk more about this next semester, actually, when we study light, because this is much more like a light wave than a sound wave. But I want you to see the similarity here. The disturbance is going perpendicular to the energy. So the energy is moving from left to right across the surface of the lake, but the disturbance is moving up and down. And actually, unless you're surfing, you would stay right in that one spot. You'd get lifted by the wave and then dropped by the wave. If you were just floating in the lake, you'd move up and down here. And the same is true for the water molecules. They go up and then they come back down again. Now, how is this similar and how is it different from a sound wave? With a sound wave, the similarity is, first of all, we have this energy being sent from left to right, at least in this example. The difference is in the way that the disturbance is moving. For the water waves, the disturbance is moving up and down, but for sound waves, the disturbance is also moving left and right. Notice what's going on there. Notice the similarities and the differences. We still have energy moving through some material. In this case, the material is the water. For sound, the material is the air. We call that the medium. It's the medium that is carrying the energy disturbance. But for water, the energy disturbance is going perpendicular to the direction of the energy. Meanwhile, for sound, the energy disturbance is moving back and forth in the same direction as the energy is moving. And that makes a different type of wave, which is best shown by this kind of a diagram. All right. So what's happening is that our sound waves, the vibration from the drum is shaking the air molecules back and forth very rapidly, hundreds of times a second in some cases. And as a result, some of the air molecules get squeezed together, and we call them the zone of compression. And then some of the air molecules get spread apart, and we say that they are found in the zone of rarefaction. Now let's take a moment to look at another diagram that I have ready for you today that I don't have ready for you. I'm sorry. I'm going to have to go find it. Let's see. It is in physical science, and it's in our class. It's in our study of waves. It's in here, and it is right here. So maybe you've seen a tuning fork before. It's a piece of metal, and it's specially made to vibrate at a very specific frequency. So you can get a tuning fork that is tuned to the note A, and you can get another one tuned to C, and another one tuned to G, and so on. When you hit this tuning fork, it vibrates very rapidly. And you can see what's happening to the air molecules. Here they are by themselves, just sitting there, nothing going on. Then you hit it, and it starts to shake them up. Let's look at this molecule right here. Does this molecule move all the way to the end with the wave, or does the wave actually pass through it? This is very much like you floating up and down on a wave on the lake. You don't move along with the wave. You don't move with the wave unless you're surfing, and then you have to try really hard to catch the wave. Similarly, these molecules do get moved back and forth. They get squeezed together in the zone of compression, which looks really dark in this diagram. And then they get stretched out in the zone of rarefaction. But this air molecule next to the tuning fork is still next to the tuning fork when it finishes vibrating. It doesn't get sent way over here. Okay, so this is what a sound wave would look like. In a way, we could compare it to a water wave. For example, maybe this is like the peak of the wave at the zone of compression, and this is the trough of the wave at the zone of rarefaction. So you could think of it like this, if this helps you imagine what's going on. But keep in mind, the drawing I just made is much more like a light wave or a water wave than it is like a sound wave. Okay, now this part of this page about cymatics is pretty cool. There's a video I want you to watch, and it's a musician playing a bunch of different instruments, and it's kind of a I would say it's kind of an electronica kind of a song that he's playing. And what he's done, and we're going to talk about this more in a second, is he's taken, for example, his speakers and he's laid them down flat so the speaker is projecting sound up towards the ceiling. And then he puts like a piece of paper on the speaker, and then he sprinkles some kind of white powder on the paper. Then when the sound waves come through the speaker, it vibrates the paper, which vibrates the white powder, and the powder ends up accumulating in these patterns. And with different notes, these patterns change. And we call this cymatics. And so there's this really cool visual representation of what's happening to the sound waves. He also does this with flowing water. So the water flows in different patterns when the sound goes through it, and he even does it with flames at one point. You could see the flames changing because of the sound waves going through there. So this is something I want you to do on your own. Very much like the world of sound video. It's going to be much better if you watch it on your computer than my trying to show it to you. And then as you're watching it, you're going to describe these different things, just those 6 questions. So this is kind of like a homework thing to do, or maybe you'll have time to do it at the end of this class. All right. So that takes us to page 10. And this one we are going to work on together. What we're going to do is we're going to look at a simulation of sound waves. And in this simulation, you have to have downloaded the simulation for it to run, which is why we're going to do it together instead of you doing it on your own. It's kind of fun to operate it yourself. If we were in class, I would do that, but since I can't really help you download it onto your computer, I'm just going to do it here, and we're going to work on it remotely. Okay? So here's what the simulation looks like. Sometimes it shows a guy, sometimes it shows a girl listening, and we can see this speaker is vibrating, and those vibrations are producing these sound waves that then reach the listener. Now, the problem that I have is that the listener, with the computer, when I'm trying to talk to you, if I'm trying to produce a sound at the same time, it doesn't work very well. So I'm running this in two computers at the same time, and that means the timing won't be quite right, but basically it's just a tone that you might find rather irritating. And I'm going to try to demonstrate that for you. Let's try again. Ah, there we go. Can you hear that?
Yeah.
Yeah, so I'm going to be turning it on and off, but this is the sound that the simulation begins with at this particular frequency, at this particular amplitude, when we're hearing what sound the speaker is releasing. So this is the sound being released by the speaker. And I'm going to pause that for a minute, just so you don't have to drive ourselves nuts hearing it. Okay, so let's go back to the project itself. Notice that when the simulation starts, you can both see and hear the sound waves. The waves are shown moving through the air, with the dark areas showing where the air molecules are squeezed together, and the light regions show where the air molecules are stretched apart. Question 1, label the arrows in this diagram with a ZC to show the zone of compression and a ZR to show the zone of rarefaction. Now remember, it says right here, dark areas show where they're squeezed together. Light areas show where they're stretched apart. So this is kind of a little quiz for you. Which of these, squeezing them together or stretching them apart, which of those is the zone of compression? Which of those is the zone of rarefaction? So here's the dark arrow. Should you label that ZC or ZR? And here's the light arrow. Go ahead and do that now. You might want to scroll up to the previous diagram that gives a hint of where these are, showing the zone of rarefaction and the zone of compression. Label those on ZC, label ZC and ZR in the correct places here. Okay. Now we're going to listen, and we're going to describe what happens when I move the person closer to or farther from the speaker. What do you think should happen? What would you experience if you moved closer to a speaker at a concert and then you moved further away?
Loud.
What do you think would happen?
It's gonna be louder.
Yeah, so you're going to answer this question, and let's see how good the simulation does this. I'm going to turn the sound back on. And again, I'm doing this in two computers at once. You're seeing it on one computer and hearing it on another computer. Let's move her really close, and then I'll move him in close. Oh, wait, I had to click on listener, huh? This is what the listener is hearing. And I move him in close. What happens to the volume when he's close? I'm going to move the listener far away. What do you think should happen to the volume far away? Go ahead and answer question number 2 while I move them back and forth again. They're in close. Move them far away. That should not really be a surprise. It just shows us that the simulation is set up well. Now, this is what the listener is hearing. For question 3, we're thinking about what is happening at the speaker itself. So if I click on the speaker, we're going to hear the sound of the speaker, and I'm going to move the person back and forth again. So here's the sound of the speaker. I move the person in. Is there any change? We're not recording the sound of the listener. We are recording the sound of the speaker. Does it change when I move them back and forth if we're recording sound directly from the speaker?
Yes.
It does? Listen again. I didn't hear any change. So let me explain that again. I'm going to turn this off because it's driving me nuts. Let me explain that again. For question 2, we're recording the sound. It's like this person has a microphone on, and that sound is being recorded, and we're moving them back and forth. Did the sound change then?
Oh no.
When I had this for question 2 on listener, it did change. Like she's wearing a microphone. Yeah, it's going to change. It's going to get louder and quieter, right? But when I put the microphone right here, does it really matter where she is?
No.
If the microphone is right there, this is question 3.
What is
Okay.
a speaker? And describe what happens when the person is moved into closer to and farther from the speaker.
Right. So that's what I've done here. Question 2, we were listening to it get louder and quieter when she moved because she had the microphone on her. Question 3, the microphone was not on her. It was right next to the speaker. Did it matter where she was? Or
Teacher,
was the speaker
when you
always
clicked
producing
on
the same
listener,
sound?
when you clicked on listener, it would and you moved it closer and farther from the speaker, it would change sound. Like the
That's
sound would.
right. And you described that in question 2.
Okay.
In question 3, I'm moving the person around, but the microphone is still here right next to the speaker. Does that change what the person hears at all?
No.
Because the microphone is next to the speaker, so it stayed the same for number 3. Question 4, explain why one of them made it get louder and quieter with number 2. With number 3, it always stayed the same volume. So explain the difference on question 4. Take a minute and do that. Hey, would you mute your microphone? Thank you. If you have any questions at any time, please unmute and ask, or you can type them into the comments too as another option. And in fact, I'm going to ask you to give me a thumbs up when you finish questions 1, 2, 3, and 4, so I know we're ready to move on. When you're working on number 4, think about what I was saying about the microphone. Here, the microphone, when I click on listener for question 2, the microphone is on her. It's like she has a microphone that she's wearing on her blouse. But for question 3, the microphone is next to the speaker. It doesn't matter where she is. I'll demonstrate this all again. Here we go for question 2. Did we hear a change when we move her back and forth for question 2? You should hear it getting louder, and then you should hear it getting quieter. For question 2, when I've clicked listener, the microphone is on her. For question 3, if I click on speaker, this is the sound of the speaker itself, and I can move her, and it doesn't matter where she is, because this is the sound coming directly from the speaker that we're hearing now. It doesn't change at all, does it? For question 3. Question 4, explain why we heard a difference between those two events. All right, do you have a question? Okay, good job, Laylee. Give me a thumbs up when you're done with that part. And then we'll start talking about amplitude. All right, thanks, Raleigh and Alondra. All right, guys, way to go.
Valley, I'm done. I'm just too lazy to put thumbs up.
All right, thanks for letting me know. Let's look at what we're going to do next. So we're going to talk about amplitude. And what I want you to notice for number 1, you describe what you hear when the amplitude control is moved to the right. For number 2, describe what the waves look like also when we take that control to the right. Then we're going to do the same thing, describe what we hear when we move it to the left, and describe what it looks like when we take it to the left. Okay? So let's go ahead and do this. We're only going to move this amplitude control. And let's put the speaker about here, I guess. And, excuse me, that was the listener. And I'm going to move only the amplitude control, not the frequency control. So it starts in the middle. What do you hear when I move this to the right? This is where it starts. Now I'm going to drag this one to the right, and I got to drag the sound to the right. And what do you hear right now? Let me drag that back down. And what happened when it went back down? I drag it to the right. What did you hear? Here we go again. And then I bring it back down again. Yeah, it got louder, huh? Now, let's do the same thing, but just watch these waves, okay? And what I really want you to look at is how dark and how light they are. So compare the difference between the zone of compression and the zone of rarefaction, and they're showing that by how dark and light they are. So this is question 2. What do we see with the waves? Do they get bigger? Do they get faster? Do they get darker? Do they get lighter? What happens to the waves? There's the change.
Lighter.
Yeah, those did, but what about not only lighter, but also darker, I think. More contrast, in other words. Let's drag it back down. See how that's just kind of gray now when I drag it back to the middle? And then I drag it to the right, and now it's very much black and white. So there's more contrast in the waves. Would you agree that this means the waves are a little more powerful, a little more intense? And not only that, look what's happening to the speaker. Let's drag it back down. How much does the speaker move here? You can see it vibrating, you can see it pulsing, but it's moving a lot here. And this is one thing you need to be careful of with your own sound system. If you turn it up too high, the vibration can be so much that it actually tears the speaker, because many of the speakers that you see, this part is made out of paper. And so by vibrating it too much, by turning the volume all the way up, that can tear it apart. Let's do the same thing for dragging it to the left, starting on question 3 now. I'm going to drag the amplitude down to the left. And what happened when I did that?
The waves disappeared.
Oh, in fact, I dragged it too far. I still want to have some sound. Let's listen.
The waves are darker.
Let's just start by listening only. This is question 3. Only listen. Here we are in the middle again. And I drag it downward. Can you hear it? So here it is in the middle. I drag it to the left. There it is. In the middle, to the left. Can you hear the difference? I'm doing this on my other computer, so you won't see anything changing. Here it is in the middle. Now on the left. We're listening, correct? For number 3. What did you hear happening? As I drag it to the left, what did we hear for number 3? Okay, now let's watch the waves for number 4. What happens when I drag it to the left? Is it easier or harder to see the waves now?
Darker.
Yeah, they kind of faded away, huh? I drag it to the right, we see more contrast. I drag it all to the way to the right, they're completely black and white, huh? There's a big difference between the zone of rarefaction and the zone of compression. But when I drag it down here, we can hardly see the difference at all. So which would you say has more intense waves?
Higher.
Higher.
I agree. With all that contrast, it shows the waves are much more intense, huh? Okay, so we should have been able to answer questions 1 through 4.
Wait, what happens in 3 again?
3 was hearing it. We were listening to my other computer.
Can
I'll
you
do
repeat
that
that
again. So, looks like my speaker is running out of battery. Here it is when I'm in the middle. And then when I drag it to the left, what happened to the sound? In the middle,
It's like it's more silent,
drag to the left.
not as loud.
Yeah, it got quieter, huh? So now we can answer 5 and 6. Does changing the amplitude change the pitch or the volume? Were you hearing it change in pitch? In other words, it was rising up the musical scale or falling down the musical scale? Or did you just hear it holding the same note and the volume got louder and quieter? So is amplitude, is that the same as pitch or is that the same as volume? That's question 5.
Is the okay?
This would be going up and down the musical scale. This would just be getting louder and quieter. What was happening? And number 6, when we change the amplitude, does that change the speed or does that change the intensity of the waves? Let's look again because we haven't really thought about how fast they're moving. If we look at the waves and I bring the amplitude all the way up to the right, do they seem to move any faster? Look at these waves.
Yeah.
Wait a second, look closely. Don't look at the speaker pulsing. Just look at the wave and how fast it's moving. Now I'm going to bring it down. Did that change how fast they leave the speaker and arrive at the person's ear?
Yeah.
Yeah, you think so? Let's count. 1, 2, 3, 4, 5, 6. I got about to 7 before that wave hit her ear. Let's do that again with another one. 1, 2, 3, 4, 5, 6, 7. I would argue they did not get any faster. How about this? Did they get any wider?
Yeah.
Hang on a second. Look at the width of the wave. If I measured that from here to here, how does that compare to when I bring the amplitude way down? Is the wave any wider?
No.
Look at how wide this wave is compared to this dark wave, this pale wave. To me, they look like they're a stripe that's about equal in size, and there's the same number of them in the same amount of space. So it's not about their speed, it's not about their width, but it is about their intensity, because this is a very intense difference between the black and the white, and this is a very subtle difference between the two grays. Okay, so think about that. Number 7. We haven't watched this video yet, so I'm going to help you with number 7. And I want to remind you that with this cymatics video, what this is talking about, the powder moving, is when he put a piece of paper over his speakers and then put powder on the speakers, the speaker vibrates the paper, which makes this powder jump around. And if we change the amplitude, if we crank up the speaker, how much do you think it's going to jump around compared to if we turn the amplitude way down? Let's look at this. Again, watch how much the speaker moves. I'm going to play it again. Here's a low amplitude. I can't really even see the speaker moving. The vibrations are so subtle. But as I increase the amplitude, what happens to the amount of movement of the speaker? How much would that make that powder jump around if it was on top of that speaker when we change the amplitude? So going back to question 7, How much did the powder move with a low and a high amplitude sound? You can kind of imagine it for yourself. If this speaker was laying flat and the sound was going up towards the ceiling at a low amplitude, will the powder bounce around very much? At a high amplitude, will the powder bounce around very much? That's what I'm driving at there. So give me a thumbs up when you're done with this section on amplitude. Oh, Evelyn, I didn't see your monkey thumb. Good job. If you have any questions about these 7 questions, please let me know. All right, Evelyn. All right, Leo. Thanks, Delaney.
Wait, what are we doing again?
We're answering these 7 questions.
No, but like, what are we doing for question 7? I forgot. It's because I wasn't. I
Okay.
spaced out.
You just tell me how much the powder was jumping around.
Oh, okay.
So imagine that this is looking, we've taken a speaker and we've laid it down so it's facing up to the ceiling. We've put this black paper on top of the speaker. We put this white powder on it, and then we play music through the speaker. How much does that powder jump around at a high amplitude? Here's the speaker. Imagine the paper and the powder on top of it. How much does it jump around at high amplitude? How much does the powder get moved at low amplitude? Look at what the speaker's doing. So that was moving the amplitude control. The next thing we're going to do is move the frequency control. And it's going to be very similar. We're going to listen to what happens and describe what we hear for number 1 when we move it to the right. Very similar. What do we hear when we move it to the right? For number 2, what do the waves look like when we move it to the right? But now I want you to do 2 things when you're telling me what they look like. You're going to describe the width of the wave, and you're going to estimate how many there are. And that doesn't have to be an actual number, just like there's more waves or less waves, just a comparison. That's going to be number 1. What do we hear when we move it to the right? Number 2, what do we see when we move it to the right? Number 3 and 4, the same thing, but we're going to move it to the left. How many waves and width? Okay. So are we ready? Looks like a lot of us are ready. And again, if you need to come back and view any of this, it'll be posted later today is my plan. So I'm going to put the amplitude in the middle, and I'm just going to leave it there the entire time, and I'm going to change the frequency, which is measured in hertz. Hz is the symbol for hertz. It's named after a scientist, Dr. Hertz, who first described this. And this number 500 means there's 500 vibrations every second. And so actually at 500 hertz, this speaker would be pulsing 500 times in 1 second. And so they've slowed this way down for us so that we can see it. All right, so I'm going to go ahead and turn my actual speaker on. Here is the sound of 500 hertz. All right, that's 500 hertz. I want to move it up to 1,000 hertz. Here we go. There's 1,000 hertz. Let's do that again. I'm going to step it down from 1,000 to 9, 8, 7, 6, 5. Here we go. 1,000, 9, 8, 7, 6, 5. Okay, so you should answer question 1 on the frequency page. What did you hear when I moved it to the right? I'll do it one more time for you. We're going to go from 500 to 1,000. 500, 6, 7, 8, 9, 1,000. Here we go. 500, 6, 7, 8, 9, 1,000. Actually, that's 900. There's 1,000. What did you hear when I moved it to the right?
The sound got squeakier.
Did we change the volume or did we change the pitch? Did we change the
It had a higher.
Yeah. So describe what you hear. Now we're going to look at what the waves appear to, what they look like, right? So question 2, when I move it to the right, we're going to watch what happens. I want you to look for 2 things. What happens to the width of the wave and how many waves are being produced? So let me take this back down to 500, start it back up again. All right, so here's the 500 hertz frequency wave, right? Look how wide they are, and look how many are being released. You can also look at the speed that the speaker is pulsing. Let's increase the frequency up to 1,000. What happened to the width of the waves? What happened to how many are being produced? How fast is the speaker going? So for question 2, describe what they look like, how they changed from here, 500, how thick are they? How fast are they moving out of the speaker? How many are coming along? And then compare that to the 1,000 hertz frequency. What happened to their width? What happened to how many of them there are? How fast is that speaker pulsing? Taking it back down to 5. Right? Can you see that there's fewer waves, but they're wider? Okay, we're going to do the same thing with question 3 and 4, but this time I'm going to bring it down to the left. Why don't you predict in your mind, what do you expect to have happen when you hear the sound as I move the slider from 500 down to 100? We're not going to go to, I think it doesn't go to 0. Actually it might go down to 10. So we'll see what happens when we bring the slider down to the left. What do you think is going to happen? And what do you think those waves are going to look like when that happens? So I'm going to bring my sliders back to 500. I'm going to turn the sound on. There's the sound at 500. And watch and listen. I don't want it at 0. I'll bring it down to like 100, maybe 30 hertz. That's 0. That means there's, oh, you can hardly even hear the 50. Yeah, we might as well just stay at 100. Okay, let's do that again. Bringing it back up to 500, approximately. There's the 500. Bringing it back down to 100. What happens when I move it to the left? What do you hear? Whoops, sorry. Bring it all the way down to 100.
Has a low pitch.
It's a low pitch, yeah. I'm going to shut that off. Now let's look at the waves. What's happened to the waves at this really low frequency? How many of them are there? How wide are they?
Very wide.
For question 4. And look at the speed that the speaker is pulsing now. Right? If I take it down to 0, there's no vibration at all. So there's no sound, no waves. Bringing it back to 100, this is how big the waves are. What happens at 500? That's how big they are. And look how fast they're coming out of the speaker. Bring it up to 1,000. They're really thin, aren't they? And there's so many of them. So answer question number 4. How many and how wide are they when I bring it down to 100? And that takes us to question 5. When we changed frequency, did this change pitch or did this change volume? Did it get quieter and louder, or did the note rise and fall? Was it pitch or volume? And question 6, did this change speed or intensity of the waves? Did they get darker and lighter? That would be intensity, with that increase in contrast. Do we see an increase in contrast, or do we just see that there's more of them coming out of the speaker more rapidly? It looks to me like they're all about the same equal amount of black and white and gray, but we're seeing them come out of the speaker faster and faster. Finally, how did the number of waves, which is their frequency, compare to their width? Okay, let's look at this. Frequency versus wavelength. The wavelength is how wide that wave is. We could measure it in centimeters. The frequency is how many of them there are in a given time period, like how many waves per second would be the number of hertz. Now look, can you see that when I have it all the way up here at 1,000, I've got a lot of waves coming, a very high frequency, right? But how wide would a wave be? If I measured this wave in centimeters, how many would that be? On the other hand, if I drag this down to 100, how many waves are there? I mean, I can count them. There's one hitting our ear, one in the middle, and one leaving the speaker. There's only 3 waves here. But how wide are they? If I got a ruler out, how wide would this black zone be? Somebody needs to turn their microphone off. So here, lots of waves, high frequency. But what about the wavelength? Isn't that going to be a small number? Then when I drag it back down here, not very many waves. It's a low frequency. But look at the wavelength. That would be many more centimeters than this other one, wouldn't it? In other words, when I change one of these, when I change the frequency, it also changes the wavelength. And what I want you to think about is if frequency increases, what does that do to wavelength? When I increase how fast they are, what happened to their width? Did they get wider or did they get thinner? Let's look at that again. Here they are. This is the high wave, the high wavelength, but they're pretty skinny, aren't they? Over here, you can barely see them anymore, but these are the low frequency. But look how big the wavelength is. They're really thick. So if it's a low frequency, the wavelength is long. A long distance from one black zone to another. That's the wavelength at a low frequency. At a high frequency, it's a short wavelength. But there are lots of them. So you should do something for that for number 7. And then we have a summary. And for this one, I want you to use common phrases to answer the first 4 questions. Loud, quiet, high pitch, low pitch. And then when you finish these 4, I want you to give me a thumbs up. We'll talk about number 5 together. Let me know if you have any questions. On question 4, it turns it around backwards. So for the first 3 questions, I used science vocabulary, and you give me a common phrase that means the same thing. High amplitude, low amplitude. What are the common phrases? Loud, quiet, high pitch, low pitch. Same thing for question 2. Take this science vocab and turn it into common phrases. Same thing with question 3. But question 4, I'm giving you the common phrase, turn up the bass, and I'm asking you to convert that into science vocabulary. That should have a 2-part answer that includes both frequency and amplitude.
Fairly.
Because on the one hand, it said turn up, that would be volume. And on the other hand, it said the bass. And so that would be the pitch that I'm talking about there. Yeah. What's up?
I need help on number 3.
Okay, I'm going to ask you to speak with a higher amplitude. What did amplitude mean? Did it mean pitch or did it mean volume?
Pitch.
Well, remember, we looked at 2 things. We looked at frequency and we looked at amplitude, huh?
Yeah.
The first thing we looked at was amplitude. The second thing was frequency. So let me just play for you a change in amplitude without a change in frequency, and you listen. Let's see, I'm going to take this up to the 500, and then I got to hit play. Okay, now I'm going to change the amplitude. I'm going to bring the amplitude down. What happened? There's the amplitude up.
Pitch. I mean, the volume.
Amplitude is volume, huh?
Yeah.
Here I'm going to hold the amplitude in one place and I'm going to change frequency.
The pitch.
So frequency is the pitch. Amplitude is the volume. Right? So what does your teacher want you to do if they ask you to speak with a higher amplitude?
Speak louder.
Sorry, I can't hear you. Will you speak with a higher amplitude, please? Number 4, turn that around backwards. You give me the science vocab to turn up the bass. What do you want to have happen to the frequency? What do you want to have happen to the amplitude? Okay, and then we got to talk about question number 5 here. It's asking about this inverse relationship. And let me describe this word inverse. First of all, means the opposite of something. Okay, so inverse means the opposite. And what I mean by that is that when we have an inverse relationship, when one thing gets bigger, the other thing gets smaller. That would be the inverse. That would be the opposite, right? As one thing goes up, the other goes down. So let's look at this diagram again and see if we can see something happening in the opposite way between frequency and wavelength. We're looking for an opposite thing. Oh, actually, this is a very good image to have because here I have high frequency. So this is a big number of frequency. It's 1,000. And over here, it's a little harder to see, but I have a low frequency. Let me start it again, and then I'm going to change it. I'm going to drag this down, then I'm going to pause it. Maybe I dragged it down too far. Yeah, I think I did. Let's put that at there. Okay, here's my low frequency. It's a small number of hertz, 240 hertz. How many waves do I see coming out of the speaker at this low frequency? Now, I drag it up to a high frequency. What happened to the number of waves? So, here I have a low frequency. Here I have a high frequency. But What do I have for the size of the waves? What is the distance in centimeters between one dark line and another? Isn't this a lot less than this is? So what do we see? When I make the frequency big, the wavelength gets small. Is that inverse relationship? Is that the opposite? Over here, when I had the frequency small, a low frequency, the waves got big. Again, we're looking at an inverse relationship. The opposite thing is happening. The bigger the frequency, the smaller the wave. The bigger the wave, the smaller the frequency. That's what we're talking about by this inverse relationship between a sound's frequency and its wavelength. So you could do something like this. Oops, I need to go here. You could start off your description something like, the greater the frequency, the what happens to the wavelength. And you could think of it as smaller and larger too. I'm just going to start a new line. The greater the frequency, the what? Would this be taller, or would this, excuse me, would this be longer or shorter wavelength? If it has a big frequency, what happens to the wavelength? Let's look again. Here's the big frequency. Many waves, high frequency, but is that a short or a long wavelength compared to these guys now? Isn't this a much longer wavelength, but a lower frequency? Here's another way you could do it. Maybe you want to do both of these, one for high frequency, one for low frequency. The lower frequency, what happens to the wavelength? And these should be the opposites of one another. As this one goes up, this one should be coming down. As this one lower is going down, this one should be going to a bigger number. If we measure these things, if we count them out or measure how long the waves are, we're going to see when one increases, the other decreases. That's an inverse relationship. They do the opposites. Okay. So I need a thumbs up when you're done with that part. Thanks, Raleigh. Okay, what we're headed towards is actually doing a lab. Thanks, guys. Thanks for letting me know where we are. Excellent. You've probably been waiting for me for a while. We're going to do a lab now. And basically what we're going to do is we're going to collect some data, and then we're going to make a graph, come to some conclusions. What we're going to do together is gather the data, and then I'm going to turn you loose to complete the graph, okay? So we're going to analyze only frequency, not amplitude, just changes in frequency. And we're going to look at 10 different frequencies every 100 hertz. And what we're going to do is we're going to measure the amount of time it takes for 10 waves to go by. The time it takes for 10 waves to go by. All right. Now, of course, this would be very hard to do if we didn't actually slow down the sound waves, but fortunately the simulation has slowed it down for us. And of course, any good experiment starts with a hypothesis. So I would like you to write a prediction about whether you think it will take more time, less time, or the same amount of time for 10 high frequency waves versus 10 low frequency waves to be released by the speaker. Write a hypothesis, fill in this blank. I predict that it will take, what, more time, less time, or the same amount of time for 10 high frequency waves to be released from the speaker than it will for 10 low frequency waves to be released. So this is what we're going to be doing. I'll just put this in the middle here. And what we're going to do is, actually, it's going to be in this section. Here's the speaker. We can see it pulsing away. We can see the waves coming out. And I'm going to start a timer. And we're going to count how many waves are released by the speaker. We got to count 10 of them. So you can count the waves coming out. You could count the wave hitting the timer. I'm going to count the pulses of the speaker. That seemed to me to be a little easier way to do it. But what do you think? Will it take more time or less time for this speaker to release 10 waves? Or will they be the same? Go ahead and fill in your prediction. And then we're going to get started with the 100 hertz frequency. We'll measure the time for 10 waves to be released. All right. So it's a little tricky, so bear with me. I was going to try to make the sound for you, but for some reason it's not working. Let's try again. No, I don't hear anything. Let me reload this while you finish your hypothesis. All right, there's the sound of the 100 hertz wave. So what I'm going to do is I'm going to take this down to 100. And we're going to count how many black stripes, how many waves are released by this speaker once I start the timer. And the way I'm going to do it is by looking at the pulses of the speaker itself. It should be the same however you count it, but that's what worked for me. So I'm going to start the timer in 3, 2, 1, and go. What? It just froze. What happened? Let's reset that. Go. 1, 2, 3, fourth wave, 5, 6, 7, 8, 9, and 10. Okay, so there's my result, 0.1033 seconds, 0.1033. So I'm going to put that over here at the 100 hertz part, 0.1033 seconds. Okay. I'm going to go back here. I'm going to reset the timer. We're going to go up to 200 hertz. There's the sound of the 200, and there's the waves of the 200 coming out. And then I'm going to start the timer. 3, 2, 1, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So there we are. 0.0522 is my result. 0.0522. Oops, that's not supposed to be an O, that's supposed to be a 0. 0.0522. Okay, I'm not going to write these down for you anymore. You're just going to have to pick them up from the simulation as we do it, okay? But that's the idea. You're going to fill in this data table as we go. So let's see. I'm going to change my frequency to 300 hertz. I'm going to turn on my sound over here and give you the sample of 200. And then I'm going to change that up to 300. I'm going to reset this. I'm going to watch the speaker. 3, 2, 1, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my answer. You're going to fill this in for the 300 hertz, 0.0341. All right, we're moving up to 400 hertz. What does that sound like? And I'm going to reset the timer. I'm going to watch the speaker pulsing. 3, 2, 1, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's your data to write down. 400 hertz, 0.0256 seconds. Moving up to 500 hertz. Here's what it sounds like. That's 400. There's 500. Resetting the timer. Getting ready to start the clock. 3, 2, 1. Oops, I missed it. 3, 2, 1. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, there's your data. Now, really, if we were going to do a really good job on this, we would do every frequency 3 times or 5 times or 10 times and take the average. Because wouldn't it be pretty easy for me to click the start button or the stop button a little early or a little late and make some measurement errors? And we can get rid of those, maybe not totally get rid of the measurement errors, but we can minimize them by taking the average of multiple trials. So that's what we really should be doing. But we're going to take a shortcut and just do the best we can to be accurate each time. All right, I'm moving it up to 600 hertz. Here's what it sounds like. Let's see. There's 500 again. Moving up to 600. Resetting the timer. Here we go. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's your data for 600 hertz. And what do you think? Am I more likely to make errors in measurement at the slower or the faster frequencies? So 0.0171 for 600 hertz. Let's move up to 700. The sound changes from 600 to 700. I reset the timer. Get ready. 3, 2, 1, 3, 2, 1, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 700 hertz, 0.0151. And then we're moving up to 800 hertz. There's 700. There's 800. Resetting the timer. And it's getting tricky now. 3, 2, 1, 3, 2, 1, 3, 2, 1, go. Oops, I don't think I did that very well. Start again. 3, 2, 1, 3, 2, 1, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.0186.
Wait, Fairly?
You didn't restart it.
I
You said
just
it.
forgot to restart it.
I forgot to restart it? Oh, I thought that number
Yeah.
got too big. All right, I'm not going to play the sound again. Do you mind?
Yeah.
1, 2, 3, 4, 5. Oh, sorry. I got to start it. 3, 2, 1, 3, 2, 1, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's better. I was wondering, that data looked a little funny to me, but since I wasn't writing it down, I wasn't sure. Thanks for letting me know I screwed up. All right, we have two more. 800 hertz, 0.0129. We got to do 900 and 1,000. So here's the 900. What does it sound like? 800 going up to 900. Reset. Okay, it's getting tough. Here we go. 3, 2, 1, 3, 2, 1, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.0119 seconds for 900 hertz. And then the last one. Here's 900. Take it all the way up to 1,000. Resetting. 3, 2, 1, 3, 2, 1, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's getting harder to measure. To start and stop it at the right time gets trickier and trickier. So I got 0.0119 seconds. Okay, now, let's talk about what your graph should look like. And then I'm going to turn you loose to finish on your own. So first of all, we have these two variables. We have frequency and we have the time for 10 waves. One of your axes needs to show one of those. The other shows the other variable, right? And the way you choose between them is that the x-axis shows the cause of the changes. That's the independent variable. Whereas the y-axis shows the results. Now, what did we start with? We started with the frequency, and then we measured the time. In other words, the cause was what we started with, the frequency. So your x-axis title should be something about frequency in hertz. Your y-axis title is what we measured, the time for 10 waves to go by in seconds. Now, what I want you to notice is that this one should be a line graph, because could there be numbers? Is it possible that there's in between numbers? Is it possible that we could have done 150 hertz? Could we have done 333 hertz? Could we have done 792.1 hertz? That would all fit on there, and that means we need a line graph. So you should not do a bar graph. Since you're going to do a line graph, you're going to be placing these points on here, right? And I don't know what they're going to look like exactly. Maybe they're going to do something like this. And once you place your points on there, of course, you have to connect them with a line, a best fit line. All right, so you need to do that. Now, the numbers on the axis, we're going to start with 100 down here, 200, 300, 400, like that, right? But shouldn't we also show that this is 0? I think so. This would be 0 hertz, and then we go up by 100 every time. Meanwhile, on the y-axis, how far do we have to get? What was our biggest number? It was 0.1033, huh? So we need, our biggest number needs to be 0.1, I think. 0.1. And we can go down 0.09, 0.08. We want all these numbers to be very even, right? So at the very bottom, we should just have 0. And the next one up should be 0.01. And we just keep going up. You could think of this as 1 cent, 1 penny, right? If this was money, that would be one penny. We just keep going up. If you need to, you might need to go to 0.11 up there. And then this would fit in just fine. Okay? So some of our numbers that we actually graph, what if we had, for instance, 0.83? Well, here's 0.8. 0.83 would be about here, right? You're gonna have to have some of those points are going to go in the middle, aren't they? Okay. Finally, you need an overall title. You need a title that describes what we're showing. And my hint to you on the overall title is that it should include both of these terms. A good way to start your overall title might be something like a comparison between, and then I'm going to leave you to write the rest of the title, between blank and blank. Something like that. Or you could say the influence of would be another way to go. The influence of blank on blank. And again, you need to include these two terms, which notice are our X and Y axis titles. Those become part of the overall title. Okay? Then you're going to come to some conclusions about your data. There's a couple questions to answer about that, and then you'll be done with page 12. All right? And that's where we're going to leave it for the day. That took a little longer than I expected. Sorry about that. But look, we got a few pages done, huh? That's a nice thing. We got 3 more pages done. So, if you have any questions about how to do your graph or about some of the questions that we answered earlier in the period, stick around. Otherwise, you are free to be on your way. Thanks for bearing with me for this long class today. And I hope you have a good weekend. Adios.
Thank you.
Bye.
Thank you, Fairly.
Yeah.
Bye,
Have a good weekend.
Thank you, Fairly.